This video is about another kind of generalized linear model, and this one is focused on data that come in the form of counts. So there are a lot of different types of data that actually fall into this category, and it's why I'm dedicating a whole lecture to it. So for example, the number of calls that come into a call center in a particular fixed interval, or the number of flu cases that occur at a specific month in a particular area of the United States, or the number of cars that cross a bridge at a particular time. Data can also come very often in the form of rates. So for example, in education studies, you might look at the percent of children who are passing a particular test, the percent of children who, say, read at grade level. Or you might look at the percent of hits to a particular website that come from, say, the United States or from Great Britain. These are percent terms that you could try to use linear regression to try to model these, but you might have some troubles with difficulties just like you had with binary data. Linear regression with a transformation is always an option in these cases, and sometimes it can be just as useful as using these more sophisticated techniques, but the sophisticated techniques are probably the default that people use when they see count data. So we're going to be using the Poisson distribution to analyze these data, and so I thought I'd just do a very quick refresher on the Poisson distribution. So the Poisson distribution has just one parameter. It's this lambda parameter, and that's the rate. And so you can imagine if the rate is equal to 100, you can imagine that the average number of calls coming into a call center in an hour is 100 with some distribution that's Poisson. And you could also have another example where the distribution has a rate of 50, so then only 50 calls are coming in on average. If you look at a histogram of the two different Poisson distributions, so one where the rate is 100 and one where the rate is 50, two things are different here. First of all, obviously the center of the distribution changes. Here it's at 50 and here it's at 100. You can also see that the spread gets a little bit bigger. So here the spread is smaller than the spread of this distribution here. And so that's because there's only this one parameter, and it turns out that that parameter controls both the mean and the variance, so both the center and the spread of the distribution. So for Poisson data, the mean and the variance are actually the same thing. So if for these simulated data, if we look at their mean and their variance, they'll be very close to each other. In the case of the rate being 50, the mean and the variance are both 49. And in the case of the mean parameter, the lambda parameter being equal to 100, you actually see that the mean and variance are both very close to 100. So that's an important point, because when we do this regression analysis, if we assume a Poisson distribution, we're making an important assumption about the relationship between the mean and the variance. And that will be true sometimes, but there will also be many times where it's not true. So the example data that we're going to be using for this is actually traffic to my website. So we'll see how embarrassing and how few hits actually come to my personal website. This is where it is if you'd like to come and add a few more hits for the next time that I run the class. So what I've done is I've actually collected this data and I put it here. This is data that I've collected using Google Analytics. And so I load this data and I actually create another variable based on the date variable that is the Julian date, and so I'll explain that in just a second. So our data set now contains the date, so this is actually the date 2011, the first day, January 1st, January 2nd, January 3rd. This is the number of visits to my site. And this Simply Stats here is actually the number of visits to my site that came from my blog, simplystatistics.org. So you can see back in 2011, my site actually wasn't even up yet, so you don't actually see any hits to my blog, or to my site, or to my from my blog, because my blog wasn't going either. And then the Julian date is actually, what it does is it just counts the number of days between the observed day here, 2011 1/1, back to 1970 1/1. So it counts the days back to between 1970, the first day of 1970, to the day now. And so the reason why I calculated this quantitative number is it's going to make it a little easier to include this term, this Julian date, actually in regression models later in the analysis. So I collected these data actually using this very nice R package, the RGA R package, which allows you to access your Google Analytics data and download it very nicely through the API. So first I'm going to start off plotting the data. So here on the x-axis is actually the Julian date. So this is the number of days since the first day of 1970. And so on the y-axis is the number of visits to my website. So you can see that it's going along very nicely. And then all of a sudden there's actually this jump here. You can kind of see this chunk. That jump is when they announced the Coursera class actually. So you can see that I have a little bump in my traffic from the Coursera site. That's thanks to all of you. So in a linear regression analysis, we could say the number of hits to the website is equal to this linear function where JDI is the Julian day. So B0 would be the number of hits to my website on Julian day 0, 1970 0101. And B1 is the increase in the number of hits per unit day. So for every day, B1 is the average increase in the number of hits. And EI, again, is variation due to everything we didn't measure. For example, in this data set, we don't have a variable indicating when the Coursera class started. So the linear regression line looks like this. If we plot, again, the data where the x-axis is Julian day and the y-axis is the number of visits to my site, if I just fit that linear model using the standard LM command where the outcome is visits, and the covariate is the Julian day, and I add that line to the plot, you can see that there's this line fits sort of reasonably well, kind of goes down the middle, and is just a linear increase in the number of visits per day. So Poisson regression, just like logistic regression, sort of changes the way that we're looking at the outcome. So for linear regression, remember we wrote this model down where the number of hits is equal to a linear function of the Julian day. That's equivalently written as the expected number of hits for a particular Julian day is equal to this linear term. So basically the mean value, we're modeling the mean value of the number of hits. So for a Poisson model, it's also sometimes called a log linear model, and the reason why it's called log linear is because if you take the log of that mean number of hits, you make that be a linear function now. So the other way that you can look at it is that the expected number of hits is equal to e to the b0 plus b1 times the Julian day. And so this actually is a very natural way to parameterize it if you think that the data have a Poisson distribution, for example. And another nice interpretation here is that you actually get multiplicative differences in the expected value. So remember that the expected value of the number of hits is equal to e to the beta 0 plus beta 1 jd. It turns out because of the algebra of exponential terms, you actually get this is equal to e to the beta 0 times e to the beta 1 jdi. So in other words, if you increase the Julian day by 1 unit, in other words, if the Julian day is one farther along, then what you do is you just take the previous expected value for the number of hits and multiply it by e to the b1, because essentially what you're getting is a increase of b1 e to the b1 units multiplying the expected value as you increase the Julian day. So this is actually a multiplicative version of a linear regression model. And so again, we can plot the data. We can plot the Julian day on the x-axis and the number of visits on the y-axis. And now we can fit a GLM object. We fit this GLM just like we did the LM object, where the outcome is the visits data on the left-hand side, then a tilde, then the covariates on a right-hand side separated by a plus sign. And remember with with the logistic regression, we said family equals binomial. Now to do this Poisson regression, we say family equals Poisson. That's how we always do it when we have these counts. And so we can then add the fitted line that comes from the linear regression, that's the red line, and the fitted line that comes from the Poisson regression. And so what you actually see is that the Poisson regression is a little bit more curvilinear. So particularly out here at the ends, it's a little bit different. So it kind of it'll like curve up and follow this along. Now, if the growth of hits in my website had been growing much more quickly, you would see that there would be a much more dramatic difference between these two lines, as the Poisson regression line would follow that curve, where the linear regression line would be sort of a linear term fit through the cloud of points. So remember that I said that the Poisson random variable had a property, or the Poisson distribution had a property, that the mean and the variance were the same thing. So you'd expect as the mean increases, the variance would increase as well. So what I plotted here actually is the fitted values on the x-axis. I'm sorry, I mislabeled it with the date. And on the y-axis, I've actually plotted the residuals. And so what you'd like to see here, if you sort of assume that the Poisson distribution fits correctly, is that as the fitted value increases on the x-axis, that the residuals get more and more variable as well, because the variance would be increasing on the y-axis. That doesn't actually hold very much true in this particular case. In other data sets, you would definitely see that mean variance relationship. So one thing that you can do is, if you don't want to make that assumption that the mean and the variance are the same, you can use what's called model agnostic or robust standard errors. I don't like the term robust because this particular kind of standard error relies very heavily on the fact that the sample size is large. It relies on the central limit theorem quite heavily. And so what you have here is an actual function that I've taken from this website, or this answer to this Stack Overflow question, which calculates confidence intervals using this sandwich estimator, the model agnostic standard errors. So it's in this package sandwich. So you need to load that library and then run this function to get model agnostic confidence intervals. And so you can run the confidence interval function on the GLM object, and you get these confidence intervals here for the intercept term and for the Julian date term. So this is the log of the multiplicative effect. So e to this term here gives you the multiplicative change in the number of hits to my site, given a 1 unit increase in the Julian day. If you do the model agnostic confidence intervals, you actually get confidence intervals that tend to be a little bit wider. So for example, the confidence interval for Julian date, it's a little bit lower on the lower bound and a little bit higher on the upper bound. And so it's a little bit more conservative, but it doesn't make that assumption of equal mean and variance. In addition to using Poisson regression to model the counts, you can actually use it to model rates as well. So for example, suppose I want to look at the expected number of hits that come to my site from Simply Statistics divided by the total number of hits to that site. So this is the percentage of hits that come to my site from Simply Statistics. I can use the same framework, the same Poisson regression framework. If I take the log of both sides, then by properties of logarithms, I actually get the log of the same expected value I was using before. Now I have minus the log of the total number of hits equals this linear term. And so I can move this term onto the other side. And so what I end up with now is the log of the expected number of hits that come from Simply Statistics is equal to the linear term plus a term without a coefficient out front that's going to be called the offset term, which is just the log of the total number of hits to my site. So now I can use this Poisson regression model to model the fraction of hits that come to my site from Simply Statistics. So what I've done here is I've actually fit this generalized linear model in R, and so what you do is it's very similar to what you did before. You use the numerator of the fraction is now the left-hand side of the model. So in this case, it's the number of hits that come from Simply Statistics. Then you have tilde. Then you have the covariates that you're including in your model. In this case, it's just the Julian date. And then what you do is you pass it the offset term. So in this case, remember the offset has to be the log because of the algebra that I did on the previous page. So here I have to pass it an offset of the log of the total number of visits. I'm adding 1 here because in this particular case, I have a lot of dates where there's 0 visits to the site, and so I have to add a 1 here so that this log term is defined. And then again, I just tell it to use the family equals Poisson. It's going to use the Poisson regression. And since I've not defined that this log of visits comes from GA data, I actually tell the GLM object where to find this variable visits. So then if I plot the fitted values, I can plot 2 versions of the fitted values. So first, in blue, what I can plot is the fitted values that I get for the number of counts to my website, where I'm fitting that with this Poisson regression model where I'm taking into account the denominator every time. And so in this case, what I'm actually looking at is the total number of hits that come from Simply Stat. So this is the fitted values for the total number of hits that come from Simply Statistics. And so you see this variation because you actually are modeling the variation into total hit count. And so you can also put a plot of the Poisson regression model where I model just the total hits. And so this is the fitted total hits using the Poisson regression model previously fitted GLM1. So another way that I could look at this is I could actually look at a plot of the date versus the fraction of hits that come from simply statistics. So here again I am looking at the number of hits that come from simply statistics divided by the total number of visits to the site. And so you can see that this number is now between 0 and 1, right, because it's a fraction. And so now I can plot actually the fitted values that I get from the Poisson regression, which are actually fitting the counts of the total number of simply statistics hits. And I can just divide it by the total number of visits, and I get a smooth curve like this that travels through the middle of the number of visits. So you can see that there's an increasing number of visits to my site that come from simply statistics as time goes on. So that's just a couple of ways that you can use Poisson regression when you're dealing with count data. They are actually much more flexible. Log linear models can also be used to model multi-way tables. So instead of just 2x2 tables, you can have tables where you have multiple factor variables and you want to identify independences in those tables. You can use Poisson regression models in clever ways to do that. You can also read on the Wikipedia page on Poisson regression more about the Poisson regression models, or about overdispersion, which is allowing for differences in the mean and the variance of the Poisson models. Although the alternative is to use those sandwich estimators we talked about a minute ago. And then here's a nice vignette on regression models for count data in R, and as well as a package that allows you to look at zero inflated models. So in some cases, it occurs that there are a lot of extra zeros that the Poisson model isn't accounting for. In fact, this is one of those scenarios because there were a lot of dates where there were zero counts. There were zero visits to the site before the site was up and running. So to model those data, you can actually use what's called zero inflated models, and this package actually has a lot more information about how you fit those models.